My guest today is Dr. Trindade Falcão, who is postdoctoral researcher at the Center for Astrophysics at the Smithsonian Institute of Harvard University. She's interested in multi-wavelength studies of active galactic nuclei, AGN, their evolution and connection to the interstellar medium. Welcome, Anna.
Thank you, Gill. Thank you for inviting me. Very good to be here.
Yeah, thanks for doing this. So we have a number of different things to talk about, some of them a little bit technical. And as I mentioned, I have no background in this, but I found it very, very interesting. And so I was going to use the review paper. I guess it was by a couple of your Harvard colleagues. And so it says here, active galactic nuclei, AGNs, are normally considered the quintessential point sources. Their electromagnetic emission is believed to be the result of the gravitational accretion of circumnuclear material, stars and gas, onto central supermassive black holes at the nuclei of galaxies. Yet they show extended structures from parsec to several kiloparsec scales in the radio, optical, and X-ray bands. So before we get to the details of this, Anna, so I want to get a feel for the scale that we're talking about. So if you take the Milky Way, we have an AGN too, right?
Yeah, so we do have a big black hole in our own Milky Way, and it's actually called Sagittarius A star. And it weighs about 4 million times the mass of the sun. And we think that nowadays, we astronomers, we think that every big galaxy around us also has a big black hole in it. So you've probably seen that famous image of the big black hole in M87, which was actually the first image that they released, and it was published by the Event Horizon Telescope. And I think that one is about 6 billion, maybe, the mass of our own sun, so quite a lot larger.
But yeah. Sorry, Anna. So the famous photograph is from M87. It's not our black hole.
The first one, it was from M87. Okay. So more recently, they released another image from Sagittarius A star, which is our black hole. But the one that got more famous was the one from M87, yeah.
Okay, so that's 7 billion sun masses, as you say, so that it's probably easier to image. So in that context, our black hole is rather small, like a few million suns.
So yeah, Sagittarius A has around 4 million times the mass of our own sun. So yeah, the one in M87 is quite a lot larger, but it is not one of the largest that we've ever seen. So I think a big question that I see sort of everywhere is that when we think about black holes, most people, they ask themselves, where do they come from? Because especially when it comes when we talk about the supermassive black holes, which is my area. So there's been a lot of work over the years studying these objects. And what happens is that these black holes, they're actually accreting material from the gas and the dust that is around them, and from the galaxies that they reside in. So when you have something, when you have an active nucleus, or one option is to have a quasar, for instance, which you may have heard, is basically a form of AGN. And these are objects, AGNs, when you have a lot of material that is falling into the black hole. So the black hole is actually growing. And in the process, this material that is orbiting the black hole heats up and radiates and produces huge amounts of luminosity and radiation. So the material, once it goes into the black hole, that's gone. But as you may know about black holes, they have this sort of event horizon, and things that are inside them have no way of escaping. But on the way in, the material can release a lot of radiation before it actually falls into the black hole. And this gives off a very characteristic set of signatures that we can use to find galaxies that have these growing black holes in them. And so, yeah, indeed, what people have done is looking at these various signatures. For example, a popular one for AGNs is to look at very bright X-ray emission. And it turns out galaxies, normal galaxies, the ones that do not have an active black hole in their center, they are not very good at producing X-rays. They usually tend to be not to be bright in X-rays. But when you have a growing black hole, that can be very bright in X-rays. And so, then,
Yeah. So can I think about an AGN, sort of the area around the black hole? Is that the way to think about it?
So the AGN is the active black hole. So yeah, the AGN is the active black hole itself. So usually we call the AGN by the name of the galaxy, but that's not correct. The AGN, which stands for active galactic nuclei, is just that active nucleus of the galaxy.
And so an AGN is really an active black hole,
exactly.
If I understand this correctly.
Yes, it's a black hole that is actively accreting material, and then as a consequence of this accreting process is expelling a lot of radiation, emitting a lot of radiation, which is what we see.
And so I know that black holes go through some sort of cycles. They become active and then they go dormant for a little while and they become active again. And so what we're calling AGN is something that presently, at least from our perspective, presently active, right?
Yes. So so there's an area in astrophysics that deals with that variability that we call it variability of the AGNs, in which you can see the black hole sort of like flickering between being active and inactive, or sometimes it doesn't really go inactive, but it goes very almost like dormant. But what we call AGNs is basically the black hole that is actively at that moment accreting material, and then once it accretes this material, it emits like huge amounts of radiation, and that's actually what we see. Because yeah, go ahead.
No, sorry. So these cycles of active versus dormant, is that typical? That happens to all black holes?
That's actually a good question. I don't know if I'm not really sure if there's an answer for that.
Yeah.
I think this is not my area of expertise, but I think it is a consensus nowadays that yes, most supermassive black holes are active. They go through these cycles of being very active, in which they are accreting a lot of material, and it's actually kind of funny because how can I put that? So the picture that we have is that the black hole needs to basically communicate some of that energy or some of that accretion energy to the host galaxy. So we know that this process is not very efficient, or as otherwise the hole could basically disrupt the host entirely, or at the very least remove a large fraction of its gas. But in this sense, if you think about it, actually, galaxy bodies, they live a very precarious existence. They're always like afraid that the black hole is going to like clear out the border of the galaxy. But for much of its life, basically the galaxy can ignore the threat that the black hole poses. But we'll see that in the end, that is always decisive if accretion continues, because basically you have, at the same time that the black hole is eating all of that material, is accreting all of that material, the way it communicates with the galaxy basically can stop that accretion. And this is what we call feedback. So the black hole grows by accreting gas, right? But in doing this, it sort of communicates some of this huge binding energy that is being released by this accretion of gas. So it communicates to the galaxy. And at the same time that it communicates to the galaxy, it pushes away material that is in the surrounding, and that sort of can stop the accretion process. So you have this cycle of turning on and off, and it's actually amazing. Yeah.
So one of your expertise is what you call the AGN winds. So this is, is sort of the galaxy evolution question. So there is a very, very small thing in the center of the galaxy that seems to be doing a lot of things, right? It seems to be, I remember this was before your time, and I remember when I was getting bored in engineering, I used to read some science books, that these big jets coming out of black holes. And it was a fascinating thing to see some of those things. And so what is our current understanding of what the black hole is doing? Is it putting materials out to the galaxy so that stars can form or whatever? But it seems like some sort of vortex, some sort of a cyclical thing, right?
Yeah, it is. And actually, it has become more clear in the recent years that basically the mass of the black hole correlates very strongly with some physical properties of the host galaxy. So, for instance, the black hole. So the black hole appears always to be a fairly constant fraction of the stellar bulge mass, and I think for me, what's even more remarkable is that when you have observations that sort of test that those scaling relations, these observations, they give a very tight relation between the black hole mass and the velocity dispersion of the host galaxy. So when I remember when I started studying that in grad school, when I first got into the AGN's part of it, that was really surprising for me, at least, these relations, because the black hole's gravity seems to have a completely negligible effect on its host galaxy, which in most ways must be basically quite unaware of the existence of the black hole. But we know that the black hole grew largely as a result of luminous accretion of gas. And these released energy far larger than the binding energy of the host. So there is a gigantic difference between these two numbers. So when you compare the energy that is released by the black hole to the galaxy versus the binding energy of the bulge of the galaxy, meaning the energy that is keeping that bulge together, we can see how the black hole mass can correlate with these properties. Basically, what happens is that the black hole grows by accreting gas, but in doing this, it sort of communicates some of its huge binding energy back to the gas reservoir in the galaxy, and then potentially limits its growth, which is what we are talking about, that cycle, and etc. And basically, the process by which this occurs is actually my area of expertise, is known as AGN feedback. And it basically takes place through an interaction between the energy and the radiation that is being generated by accretion onto the black hole, and the gas that is just laying there in the galaxy. So, and there's the AGN winds. That's where this concept comes around, because the possibility that arises is that when you have this intense flux of photons and particles that are being produced by the active black hole, these photons, they can sweep the gas bulge clean of interstellar gas, basically. So it can stop star formation in the galaxy, and it can terminate the active nucleus through that lack of fuel. Yeah.
Yeah. So let me try to understand this little bit. So there is a very small area. So
Yes.
in Sagittarius A, what's the size of Sagittarius A? It's like a solar system size or something?
You mean the size of the black hole compared to?
Yeah.
No, actually, the size of these supermassive black holes compared to the size of these galaxies, it's almost like you are comparing the size of a coin to the size of the moon. Like, they are very, very small compared to the size of the galaxy. And as I said, most of the times the galaxies don't even notice they are there. But then once this process of accretion and this process of feeding the energy back into the galaxy occurs, that's where things change. That's when the galaxy starts to notice that active black hole.
So it's very small. So in terms of parsecs, so I can quite remember. So Milky Way is like 26 million light years or something like that. Something along those
I
lines.
don't really, yeah, something along those lines.
And then the black hole itself, it's a few light days, maybe.
Yeah, it is. It's tiny. It's really tiny.
Few light days. So it's sitting there, but it is there's a lot of effects. So we have these jets coming out. It seems like very high energy. These are not particles. These are not gas or particles, but these are like X-rays and things like that.
Yeah. So I like to say that there are two main ways that the supermassive black hole binding energy can potentially interact with the galaxy. So by far the larger is direct radiation. So basically, after all that, this is how all the accretion energy is initially released. But we know from observations that most lightscapes are relatively free from the AGN. And then that suggests to us that radiation is in general not the main way the black hole affects its host. Then the second form of coupling the black hole's binding energy is through mechanical means. And then basically the huge supermassive black hole accretion, that process drives these powerful gas flows into the host galaxy, and then making collisions and basically communicates its existence to the galaxy.
So accretion means things are trying to go in.
Yeah.
But it's also what's the right term? Expelling gas. These are ionized gases that it is expelling. So there's some sort of vortex of sort.
Well, so basically what's coming out of the black hole is just the radiation. It's just the energy. But the picture behind the picture that we have nowadays behind the idea of active galactic nuclei is that you have a central black hole that is surrounded by an accretion disk. Basically, when that black hole is accreting material, that material starts to basically spin around the black hole until it falls into the black hole. So that's what we call the accretion disk. And then you have thermal emission from the disk that accounts for most of the optical and UV continuum that you see, that we astrophysicists see. So when we look at the black hole and we see some optical continuum or UV continuum, that's probably thermal emission coming from the accretion disk itself, not the black hole. Yeah. And there's also an outer part, what we call the broadline region, and a little outer, that's what we call the narrow line region. And basically, you enter into that theme of unification, and then you have the torus. But that's the general idea. You have a black hole in the center and then you have a accretion disk around it, and some of the emission is coming out of that accretion disk. When material is falling into the black hole, it just gets hot and it emits radiation.
So statistically, if you look at a large swath of the sky, what percentage of the galaxies do we see carrying an AGN?
Well, I think this is a tricky question because, as I said, these black holes, they're tiny compared to the size of the galaxy.
Yeah.
But sometimes the energy that they are expelling can be so huge that the luminosity that is being emitted coming out of that can just outshine the entire galaxy. And that's what we call most like quasars, basically, which are these very, very luminous AGNs. So physical size, they're very small compared to the size of the galaxy, but they can become active in a way that they would outshine the light that is coming from the galaxy, the light that is coming from all of the stars in the galaxy together. So that's basically when we see these things, when they are like shining. Yeah.
So if you look back in time, so I understand that quasars are much higher redshifts. So presumably they're much further out in time. The percentage of AGNs that we see in time, has it declined over time?
Well, I think that's what came first, the chicken or the egg? Because we never know, like, what came first. Like, do the black holes form first, or do the galaxy form first? But what we know nowadays is that this question of what came first is still very much open to debate. And there's still a whole bunch of different theories that posit certain interactions between the growth of the black hole and the growth of the galaxy.
It's a chicken and egg. It's a chicken and egg question. Yeah.
It is a chicken and egg question.
Yeah.
And I don't really think that's totally settled yet. So, I mean, I don't think anyone to date has found a true sort of like solitary quasar by itself without a galaxy. But that, of course, should be like a smoking gun for the earliest growth of black holes. And the fact that maybe black holes do lead this process, but there's a lot of new potential observations that will help us like tease this out, not only from a sort of direct observation perspective, but also in a statistical sense, by observing that the very first galaxies in the universe. So if you look at most massive black holes, this is actually a topic that came to like the spotlight once James Webb Telescope started like its operations, because with James Webb we can sort of like look further back in time, and we can see the very first galaxies, the very first black holes that were formed. And there is this, so once the black hole starts getting pretty massive, they pretty much have to have a galaxy around them, right? Because the supply of material that is going into the black hole is also forming stars, and there's got to be some symbiosis there, once they start getting pretty massive. But it's a really interesting question, and this gets to sort of some of the really exciting stuff for what now James Webb is doing. So if you look at these black holes, the interesting thing, and here I'm talking specifically about supermassive black holes.
Yeah.
There is one very interesting thing, is that there wasn't enough time in the history of the universe for them to form from a small black hole. And actually, we know, by the way, when we ask how black holes originate, we know there's for sure one way that can happen, which is basically you have a massive star that reaches the end of its life and then blows up, and then the core collapses into a black hole. And so that can give you a black hole of sorts of like tens of times, maybe 100 times the mass of the sun. So from the very most massive stars, they could potentially produce a black hole like that. But if you take a black hole of that mass, it can't really grow using the standard methods of accretion that we think about into one of these really supermassive black holes that we have, that we see nowadays. It's just early in the universe. There's just not enough time. So nowadays, another possibility that people have proposed is that these supermassive black holes, they didn't actually start out that small. They actually start out significantly more massive. So like, I don't know, 10,000 or 100,000 times the mass of the sun. And this way it's been proposed for their work is you have to have this kind of fine tuning in the physics that you need in order to actually allow that to happen. But the idea is that in the very early universe, you may have an overdensity of this dark matter. And inside of that, have a sort of, I think they call it pristine cloud of gas, and under exactly the right conditions, that whole gas could all at once become unstable and just fall down into a black hole that can be massive. It can be, 10 times, 1,000 times the mass of the sun.
Yeah, so multiple things are going through my mind. So is this some indication perhaps we got the age of the universe wrong? So that's one question. Secondarily, the black matter could be a big deal here, right? So isn't that a big consideration here, how they could have formed?
Well, I think one answer for sort of both of your questions, because the problem when you deal with black holes is that they are so simple. Like, and because they are simple, they don't really leave any evidence of how they formed. They don't give us any clue or nothing as like what happened in the beginning of times and how they came about. So, for instance, if you look at galaxies, we have the equivalent of like the fossils. Basically, actually, there is a field, and people call it galactic archaeology. And where the stars, old stars, the ones that were formed early in the universe, they're still there. And then one can look at our Milky Way, for instance, and you can look at the ages of all of the different stars and actually piece together its history.
Yeah.
Whereas for black holes, as I said, they are actually one of the simplest objects in the universe. The only properties, physical properties that black holes have are basically their mass and a spin. So
and charge sometimes.
Sometimes, but actually, I think for physical black holes, we don't think, unless they have charged them. So, but I don't think there is much information to that.
Yeah.
But so if a black hole formed, and all you can observe basically its mass and its spin, you don't really know, right? And most of the time, by the way, spin is hard to measure, how fast they are rotating, etc. But most of the time, you can only measure their mass. And how exactly where that came from is really hard to say. So by the time you get to more nearby black holes, more nearby to us in the universe, basically later in cosmic times, the history of these black holes is mostly erased, and we don't have any way of telling whether they started out as, I don't know, 100 solar mass object or a 10,000 solar mass object. So one of the best ways is basically to watch those systems growing, like doing it. But yeah, so I think if black holes just gave us some more clues of their history, I think it would be easier for us to maybe answer that question. But we don't really have a lot to work with.
Yeah, it's an interesting area. So I want to talk a little bit about the quasars. So if I understand this correctly, they have very high redshifts typically, and so they're going back in time. Is that true or no?
Yes, you can see some nearby quasars, but yes, but the peak of their activity was at redshift, I would say between 2 and 3. Yeah.
Yeah. And so that's going back in time quite a bit. And I remember reading something about this in the 80s and early 90s that so what does quasar stand for?
So the quasar name basically came from, I think it comes from a quasi-stellar object, basically.
Right. So I want to ask you. So they want to move away from quasar, the term quasar, to QSO, which stands for quasi-stellar object, on the premise that we find things that's not very radioactive. And so there was a broader. So have we gone back on that, or is still QSOs are still there?
Well, in our field, we basically, there are three main, I think you could say that, three main types of AGNs, basically. So you have what it's called Cipher galaxies, and they are actually apparently otherwise normal galaxies that have abnormally bright central cores. And this was actually identified by Cipher in 1942 or 3, I would say. So they identified a handful of these objects. And when they look at the spectrum of these objects, or the spectrum of their cores, they saw some unusually blue spectrum with very strong broad lines. So this is one type of AGNs. So Cipher galaxies, which are basically normal galaxies, but with a very bright central core. Then you have radio galaxies, and those were actually discovered when radio astronomy had progressed to where the accuracy of radio source positions basically allowed us to identify or to identify the counterparts with the optical. So when you look at these galaxies, they usually show a double-lobed structure, so those very extended jets that you were talking about, actually. And actually, sometimes their sizes, they can be larger than the galaxy itself. So that's actually really interesting. And then the third one is a quasar. And those were also discovered in radio surveys, I want to say. But those were a little bit trickier because astronomers didn't really know what they were looking at.
Hmm.
So some radio sources, actually, particularly those sources that are at very high galactic latitude, they before were identified with star-like optical sources.
Yeah.
Even though there often appear to be like a fuss around these objects. So meaning that they were not really completely star-like. But then when you looked at the optical spectra of these quasars, the scientists were very confused, but they were clearly not normal stars. And that's where the name quasi-stellar radio sources came from, and then it just contracted to quasar. Yeah.
Yeah, so thinking about this a little bit, so I don't think I'm thinking about this correctly. So radio waves have very long wavelengths, right? Typically, that's the case. And so, say about X-rays or gamma rays, very short wavelengths, high frequency, you associate energy with low, small wavelengths and high frequency. But these highly energetic systems producing radio waves seems a little bit counterintuitive. So what is maybe I'm not thinking about it correctly.
I'm not really sure what you mean.
So radio waves, long wavelength waves compared to very short wavelengths like X-rays or gamma rays or something like that. Yeah, in a very energetic system, you typically get very low wavelength, high frequency waves or radiation. But we see this radio waves coming out of this potentially highly energetic systems, right? Where they're radio sources.
Yeah, so when you look at an AGN from different wavelengths, which is actually one of the things that I particularly like the most about what I do, is to look at these objects from different perspectives, and then we can build like a very nice idea of what's going on. But most of the times, the different wavelengths, the different types of lights, they come from different structures in that system. So we are talking about the accretion disk. So the optical light that you see, the UV that you see coming out of that central part, comes from the accretion disk. But then when we talk about X-rays, I think nowadays it is thought that the X-ray emission of these systems come from something called the corona, which is sort of like a lamppost above the black hole itself. So when you look at different wavelengths, you're looking at light and energy that is coming from different parts of the system.
Oh, okay. So this is a multi-wavelength thing that you are very interested in. So am I thinking this correctly, that the further out you go from the center, at the center you will have very high frequency, low wavelength things like X-rays or gamma rays. The further out you go, it's going to change. So in some ways, if you look at the whole spectrum, you can we use this to measure the size of the thing?
You mean to measure the size of the black hole?
The black hole, yeah.
Yeah. So actually, the way that this is done is through something called. Okay, so let me rephrase that. There are many ways that one can estimate the mass of a black hole. In the case of AGNs, these masses, they are generally determined by this reverberation mapping technique that I mentioned. And basically the way it works is this technique measures the size of what we call the broadline region, which is basically the region that is right after the accretion disk.
Mhm.
So this technique measures the size of that region. And the way it's done is that they determine the time delay between the continuum and the emission line variations due to this light travel time across this region. So when they combine this with the emission line width, they can determine the mass, the enclosed mass that is responsible for disturbing this gas and causing this time delay. Yeah. So these are the, let's say, the best ways and the safest way to measure or estimate the mass of a black hole.
Yeah, so I'll talk a little bit about obscure AGN. So it's sort of related to the other thing that you study, which is quite interesting. So if I stand here and I observe, and I haven't seen an aircraft before, and observe an aircraft coming toward me or flying sideways or going away from me, I will have different pictures of what the aircraft might look like. We are sort of in a similar situation here, right? We are seeing things that are at a different angle, and it looks like we have put some names on them as types and things like that. But ultimately, it's a question of perspective, isn't it?
Exactly. So that comes to well, I think nowadays this sort of being disputed, and every day I actually see more and more papers that are trying to dispute that. But there's something called AGN unification. Basically, it's trying to do, like, the best description is likely to be the simplest one. Basically, in other words, we want to explain this broad range of observed AGN properties that we see in types with as few parameters as possible. So as I said, the picture that we have here is that we have a black hole in the center that is surrounded by this accretion disk. Then you have that broad line region that produces those broad emission lines, the ones that are actually used for reverberation mapping. And then you have the outer edge of this broad line region seems to be defined by what we call the dust sublimation radius. Basically, it's the nearest point to the central source where dust can survive. So this radius also defines the inner edge of a mostly opaque dusty structure that is usually described as the torus. And this is actually the key ingredient in this AGN unification, because what this proposes is that basically, putting into very simple terms, this proposes that all AGNs that we observe, they are the same. But the only difference is that we are observing them from different angles. So basically, if we observe this system from a vantage point, basically along the system axis, we are going to see basically head on. That we see the radiation from the central source, and we see the broadline region, which is inside the torus, and we see the narrowline region, which is actually outside of the broadline region. And we would call these type 1s. Basically, type 1s are these objects that are seen head on. On the other hand, if in the system plane, if we are looking, if we see only the narrowline region directly, and we don't see the central source, we don't see the broadline region, basically we are seeing it side on. So basically, I like to think of the torus like a donut. It's a donut like that. So if I'm looking, and the black hole is here, and I'm looking side on, that torus is blocking all of my vision of the black hole, basically. So this is what the unification model proposes. Basically, all of these AGNs are the same, or they have the same structure, and we are just looking at them from different angles. So yeah.
Yeah, so when we look at galaxies, we had this intuition that we are looking at them from different angles. And I wondered why it took this long for the unified AGN idea.
Well, this is actually not new. The unification model was proposed, I want to say, in the 80s.
Okay.
And as I said, it was sort of like a way to try to simplify things. So nowadays, however, there are other models that being proposed, but nothing that has been accepted fully by the community. So my personal opinion is that we are probably dealing with a combination of both. There are probably some sort of like angle dependence, but also I think the universe is too amazing and big to just give us the same kind of system, and then produce all of these different outputs. So I really think that there is this kind of like angle dependence, but I believe there's more to it. Yeah.
But as you say, if the black holes are very simple, mass, spin, and possibly charge, could we have the same thing for an AGN? In other words, so let me say what I'm trying to think. So are there parameters that is sort of related to the size of galaxy, the age of galaxy, as AGN, that we could potentially have some predictions on? Is that possible?
Well, there are many studies that try to relate some specific characteristics of galaxies that host some types of AGNs in the AGN itself. But basically, nowadays, what we know is that, well, I know this is not a super enlightening picture, but what basically this picture tells us is that the bigger the galaxies, the bigger the black holes that we have.
Yeah.
So there's this just, I don't know, overall connection in maybe the bigger things grew early in the universe and they grew rapidly in the universe. So there's more material and there's more gravity, which like helps to pull that material.
Sorry to interrupt. Is there some sort of ratio between the mass of the black hole and the mass of the galaxy?
So there are actually what we call scaling relations. So it is actually well accepted fact nowadays that the mass of the black hole strongly correlates with different properties of the galaxy. So the mass of the black hole it's always fairly constant, is a fairly constant fraction of the stellar mass of the galaxy, and then you have some correlation between the black hole mass and the velocity dispersion of the host galaxy. So all of these things tell us that the black hole, even though it's very small compared to the size of these galaxies, they can have a gigantic impact of like how these galaxies form and evolve. And we believe that this impact is through AGN feedback.
Yeah, so this goes back to the feedback mechanism. And so if I understand this correctly, it's still a chicken and egg question here, but leaving that aside, the black hole appears to have a significant effect on the formation, not necessarily the formation, but the evolution of the galaxy, right?
Exactly. Yeah. So as I said, basically, what dictates that is how the black hole is coupling that gigantic amount of energy, how it's translating it to the galaxy, basically how it's coupling it to the galaxy. And the mechanical way that you can do is you can do jets, which are the very extended radio jets. The thing about jets is they are highly collimated flows. So basically they're like a beam of light.
Yeah.
And basically to turn these jets like into a way of like affecting most of the bulge, it would require a way of making the interaction between the jet and the galaxy sort of like isotropic. Maybe changes of the jet direction over time, we don't know. But another form of mechanical communication, which actually automatically has this property, is what we call the AGN winds, which is what I do nowadays, basically. Yeah. So you have these winds, they're not as powerful as the radio jets, and they do not extend as further out, but they are more isotropic. They can affect the galaxy more isotropically. Yeah.
So I was wondering, so Sagittarius A, does it have any effect on the solar system? Can we measure anything? We are sort of 2/3 in one of the limbs. Can we measure anything?
So I don't think Sagittarius A is active now, but I would have to check that information. But if it's active, it's almost dormant. So no, I don't think we would see or we would feel any sort of like effects of that black hole. Yeah.
So you think Sagittarius A is dormant now? Is that true?
Yeah, I don't think Sagittarius A is active in the sense that it's affecting us in a way that it's noticeable.
So if it were in an AGN and very active AGN, let's say, then could it actually influence this far out into the solar system in some way? Do we know?
Well, as I said, it depends on what kind of feedback mechanism you have. So if you have a galaxy that has these radio jets, they can extend like outside the galaxy itself. They are really, really big. But the winds, and that's actually a problem, I would say, is that we know all of these nice things about feedback, AGN feedback, and how important AGN feedback is for like the evolution of galaxies, evolution of the universe itself. But when you look at winds, which are actually much more common than radio jets. So actually AGN winds, some studies say that they exist in all AGNs. And actually radio jets, we only see them in about 5 to 10% of AGN. So they're much less common than winds. But when you look at these winds and you actually measure or estimate how much power they carry into the galaxy, it's not that easy to find winds that are actually powerful enough to efficiently like deliver this feedback. So this is sort of like we know it has to exist in theory, and there are winds that they travel fast enough, and these are actually called UFOs, ultra fast outflows. These can reach.
You guys have to find different acronyms than that.
I know. Yeah, I know. Every time I'm giving like a talk or something and I talk about UFOs, people are like, but this is just ultra fast outflows. These are actually outflows winds that they can reach 0.1 C, basically 10 of the speed of light, which is extremely fast. So when you have these winds going super fast, you probably have enough energy to affect the host galaxy.
The whole
But
galaxy,
yes, to do something, to affect the galaxy somehow. But actually, when you look at ionized winds with, for instance, Hubble, which looks in the optical, the winds that we see with Hubble, for instance, in the nearby universe, they are, I don't know, they travel around 1,000 kilometers a second. So they are just not fast enough. So then there you have this problem, like AGN feedback is necessary in all of these models, in all of these simulations, but it's really hard to really like find observational evidence of it in the nearby universe. Yeah.
So all the pictures I have seen, I haven't seen too many of them, but the radiation jets are always perpendicular to the plane of the galaxy. Is that true, or that is just a...
Well, I have to say that, again, this is not my area of expertise, but I would say no. I would say that I don't think there is a preferred alignment between the direction of the jets and the axis of the galaxy. You just see them, they just extend so far out that they just look like they're perpendicular. Some of the times they are, but not necessarily.
Excellent. The only thing that we haven't really talked about is the obscure AGN. So I think there's a lot of stuff out there that we cannot see most of them, right? Is that the idea?
Yeah, basically obscured AGNs are what the name says. They are obscured. So if we think in the unified model, they are obscured by the torus of dust and gas. But the truth is that they can be obscured by something else. We don't really know what it's obscuring them. They're just obscured.
It could be it could be the galaxy's gas and stuff, right?
Yeah. It's just something in our line of sight that is basically hiding the central engine, the black hole, from us. And
that's true.
It's actually tricky to do.
Sorry, so that's true with all electromagnetic spectrum. Can we find them with something like X-ray or ultraviolet or something? But it's true with all.
So there's two biases that are involved here that make it hard for us to basically see the whole picture. One is that when we observe a galaxy, we're observing that galaxy at a very specific time, which is the time that the light takes to reach us. And we are observing it from a very specific orientation, as we talked about. And so we are here on Earth. We can't, like, I don't know, fly over and go to and see the galaxy. Well, I like to think so. But now we can do that. So what you see is basically the time scale is the issue here. Like the time scale, some AGNs, there are studies that say that all AGNs, they were obscured at a time of their life. Let's put it like that. But for studying obscured AGNs, because there are obscured AGNs in the nearby universe. So when we look at them, we don't really see the continuum that is coming from the central source. We don't see that optical emission from the accretion disk. So the way that we look at them is through X-rays, basically. So when you're looking through gas and dust, a lot of the signatures that we would normally expect to see, like the UV and the optical, all of those, they get absorbed by that gas and dust
Right.
that is like obscuring the AGN. But other signatures like mid-infrared or radio or hard X-ray emission are things that actually can penetrate. So we use our hard X-rays, high energy X-rays, like the ones that, we go and then you take an X-ray of your hand. So those can penetrate through this very obscuring gas and dust.
I see, yeah.
And actually piecing that all together turns out to be quite a lot more complicated than you might expect, but yeah.
Yeah, we're constrained by space, time, and perspective. And that gives us different ideas. Excellent. Yeah, thanks so much for spending time with me.
Thank you. Thank you for inviting me, and thank you for having me here today.
Thank you.